So Erwin Schrödinger proposed an equation that describes both of these aspects. So he proposed an equation, and this is a very useful equation if you know calculus and take PChem. Propose the equation to describe both the wave and the particle behavior. So how is it moving? Where is it going? Sometimes it looks like a sine wave. Sometimes it doesn't, but we can actually calculate that. So the equation describes the waveform of the electron. Okay, so waveform of the electron. Like it could be a sine wave, so I'm going to write like a sine wave. Okay, so waves we know move like this, but we might be able to tell if it's like a sine wave or a cosine wave or something like that. And also the position. So in space, so position in space. So the waveform part is like its velocity, like how it's moving. And the position is that what we were talking about before. We can't know both the velocity and the position. This position is like it will have X, Y, Z coordinates in space somewhere. Okay. And again, that's more of like a Calc 3 thing. So this is all kind of more of a thought experiment for us. We're not going to do all the math behind this, but we're going to look at where are those electrons. Okay, so by lots and lots of experimentation, we've been able to figure out where that probability of those electrons are, and that this equation, which I'm not going to give you, comes into play and actually describes where those electrons are. So we are going to describe electron space. So what we use to describe where electrons are called quantum numbers. Okay, so quantum numbers, and there it's got every electron has a set of 4 quantum numbers. They are these. These describe where an electron is. Describe where an electron is probably in 3D space. Okay, so all of these numbers essentially are ways to describe an area where we are most likely going to find a specific electron. Okay, so kind of bear with me through this. We're going to get through all of these, and then I'm going to help you figure out quantum numbers for things. So there's the principal quantum number. This one's pretty easy. This is the energy level, or that N that Bohr was talking about, that an electron is in. Okay, so the principal quantum number, N, is the energy level. Okay, energy level. This is like from the Bohr model. Okay, so we've really only gotten up to like 1 through 7 energy levels on all the atoms that we have created. Hypothetically, there could be an 8th energy level, but the laws of physics kind of fall apart when we get up there. So there's really only 1 through 7. So they are all whole numbers. So these are all going to be integers, 1 and up. Okay. Again, our periodic table only goes to 7, but we're going to talk about how to figure that out. So principal quantum number tells you the energy level in which an electron is. The azimuthal quantum number, which is, this is a cursive L. I tried to find the best cursive L that I could. This tells you the shape of the orbital. Shape of orbital. These are not all circular like you might think. They have different shapes of where that electron might be. Okay, so I'm going to write not all spheres. Okay, and they've determined these both by testing and mathematically. So these are not 1 through 7 or whatever. They're still integers. All of these are integers. Okay, and for each energy level, they go from 0 to n minus 1. Okay, so if we're in energy level 2, for example, so if n is 2, then that means the possible azimuthal quantum numbers would be 0 and 1, because I can only go from 0 to n minus 1. So I'm going to practice this, I promise. Like this, I just bear with me for a minute. Okay, so there's the principal quantum number, then there's the azimuthal quantum number to describe the shape of the orbital. Then there's the magnetic quantum number that describes the orientation of the orbital in space. Orientation of orbital in space. So is it going to be like up and down or pointing at you or side to side, like XYZ type of thing? Okay, so this is the orientation. And these are all integers also. Everything is an integer. But it can be negative L or negative azimuth, whatever your azimuthal quantum number is, up to 0 and then to positive L. So there's actually multiple magnetic quantum numbers for each electron that we're talking about. Again, I will get there for an example, I promise. And the last one describes the spin of an electron. Describes spin, of the electron. Okay, it's either spinning one way or it's spinning in the opposite direction, and we call these +1/2 or -1/2. Okay, so essentially what these are, they are a set of 4 numbers that describe where an electron is. It tells me what energy level it's in, it tells me what shape that orbital is, it tells me the orientation of that orbital, and which way the electron is spinning. We just use numbers to represent all of these things. Now, to make it even more complicated, or maybe to make it easier if you've taken chemistry before and remember electron configurations, all of the azimuthal quantum numbers actually have letters, at least the ones that pertain to our electrons. Okay, so instead of 0 and 1 and 2, we actually use S and P and D, and those are our letters. So if you go to the next page, Logan, if you go to the next page, the value of L, okay, so the azimuthal quantum numbers, the shape of the orbitals, we actually use letters. So these are the azimuthals. Okay, and if it is in L0, that means it is an S shape. If it is L1, that means it is a P shape. L2 is D, and 3 is F. Okay, so they go in this order. So there's an S, a P, a D, and an F. We haven't discovered anything beyond that because we haven't made any.
Do they have to be all lowercase?
Yes, they do. Good question. Yes, so all lowercase. They do have meanings like why they're S, P, D, and F based on their shapes, but you don't have to know what those are. S is S because that one is spherical shaped.
Good. Up.
Did you have a question, Hong?
But I don't know how to ask this.
Okay.
So electron just stay in
Yeah.
S.
They really do. So they stay in that whatever is describing their space. But they're not like staying still, they're just somewhere in that space.
They can jump from S to P to D?
Yes, so those are called excited electrons. So if you put in energy, an electron can jump into a different orbital, yes.
So like that's what's happening with the neon gas, for example, when you're exciting it.
Exactly.
Okay.
That's like maybe I had one that was in an S orbital and I added energy in and it jumped into a D orbital or something like that.
So is it possible that an atom can just lose all the orbital, like the P level just suddenly just gone?
The
Could they
electrons
also-
in the P level?
Yeah, they just all.
They won't leave unless there's something that attracted them to leave. So like if there was another atom attracting them, you can't like put energy in and cause them to leave. You can, I guess you can break them off essentially. If you give them too much energy, then they'll eject.
Okay, so you could technically strip an element of all of its electrons by super exciting them.
Theoretically, yes.
That's never happened, right?
It depends on the element. It's very easy to take one electron off of hydrogen, but if
Yeah,
you try
I
to
mean-
take all the electrons off of like bromine, not gonna happen.
Okay.
Absolutely. Those were great questions, guys. Okay, so big picture wise, and like I said, these quantum numbers are kind of hard to like wrap your head around. If you are looking at like you're trying to figure out all the quantum numbers in energy level 1, okay, so N is 1. Okay, I want to know the possible quantum numbers for the L or the azimuthal. And if you look at the rules, L is from 0 to n minus 1. Well, if n is only 1, that means from 0 to 0. So there's only one option, and that is L equals 0. Okay, and so that means it is S. And then you look at the next one after the azimuthal quantum number, and the azimuthal quantum number then tells us the magnetic quantum number, which can only be negative L all the way through positive L. Well, if my only option for L is 0, then the magnetic quantum number is also 0. That's all I can have. And then in each of those orbitals, you can have either a spin of 1/2 or a spin of negative 1/2. And that tells you the two different electrons in that orbital. So once we get past these quantum numbers and we look at the periodic table, this is probably going to get a little bit easier. So in the second level, you just use your rules to figure out the options. Okay, so essentially, why do these quantum numbers matter? Well, all electrons are different, and that's why these quantum numbers matter. So the Pauli exclusion principle says that no electron can have the same 4 quantum numbers. Meaning no electron in an atom is the same, okay, which makes sense, right? They're not all going to be in the same space and occupying the same space. Each orbital can hold 2 electrons, but the electrons are different. One is spinning one way, one is spinning the other way. Okay, so if I have neon has 10 electrons on the periodic table, that means it's going to have 10 different sets of quantum numbers. So 10 sets of quantum numbers. Okay, those numbers go, you first list the n, the energy level, and then the azimuthal quantum number, and then the magnetic quantum number, and then the spin quantum number. So like this set of 4 numbers tells me where each individual electron is. Okay, so how these numbers work. If I say, give me the quantum number for this specific electron. Okay, so for the quantum levels of n equals 1 and n equals 2, it says provide all the possible sets of 4 unique quantum numbers. Now, if you are able to look at both this page and page 7 at the same time, that might be helpful. But what I'm going to do is I'm going to hopefully try to like scroll back and forth. So I'm going to look at energy level 1. And actually I did this above, but I'm going to show you how we did that. So for energy level 1, okay, I'm going to list a set of 4 quantum numbers for an electron in energy level 1. So, well, n equals 1 is definitely starts with 1, right? N equals 1. That's the energy level I said that I'm at. That's my only option for n. Okay. The next one is my L, or my azimuthal quantum number. So if you go look up at the rules, L can only be the integers from 0 to n minus 1. Okay. So, well, n is 1. So n minus 1. 1 minus 1 is 0. So my only option for L is 0. So I'm going to label these. This is N. This is just for your benefit. This is L. That's my only option in energy level 1 for L. Now for my magnetic quantum number, I'm going to go look back up at the rules. For this one, it's negative L all the way to positive L. Well, my only option for L was 0. So my only option for the magnetic quantum number is 0. Okay. And then the last one is spin, which is either plus 1/2 or minus 1/2. So the only thing that can change is this is either 1/2 or it's negative 1/2. So the only 2 sets of quantum numbers for energy level 1 are 1, 0, 0, 1/2 or 1, 0, 0, minus 1/2. There are only 2 electrons that can exist in energy level 1. Now, energy level 2 is different, okay? Energy level 2 has more options for its quantum numbers because it can go up to a higher n. So I'm going to list, so we did energy level 1, so energy level 2. So that means my n is 2. All right, let's look back up at the rules. If n is 2, then L can be between 0 to n minus 1. Okay, so n is 2, 2 minus 1 is 1. So that means that my L can either be 0 or 1. Okay, so it's going to be 2, 0. I also could have 2, 1. Those are my 2 options. Okay, well, then after my azimuthal quantum number, my magnetic quantum number can be between negative L to positive L. Okay, negative L to 0 to positive L. Well, Up here, L is 0. So it could be 0. L can also be -1 or 0 or +1. So now we're starting to get a whole lot of combinations here. So if it's 0, it can be 0. If it's 1, it could be -1. It could be 2, 1, +1, or it could be 2, 1, 0. Those are all of my L options. So these are all of my options for the first 3 numbers. And then the last number can either be +1/2 or -1/2. So I'm going to make all these +1/2. And then they can also be -1/2. So essentially, I can have 4 more quantum numbers, all the same. It's just the last one is going to be -1/2. So I'm not going to write them all out. So plus 4 more, just -1/2. So energy level 2 has
Would you-
8 total possible quantum numbers.
Would you mind going
Yes.
over the third column, the magnetic quantum number again?
Absolutely. Okay, so this one was L, right? So we said the azimuthal was between 0 and 1. So it's either 0 or 1. Okay. Now, ML, magnetic, rule is between -L to +L. So for this first one, if L is 0, my only option is 0, right? But if L was 1, because we said it could also be 1, then it can go, L can be either -1, 0, or +1.
So
So I did those.
why
here.
couldn't, oh, I see, because the first one is 0, so then that can only be 0. So that's why
Yes.
you don't do the one with, okay.
Oh, and
That is
also
exactly it.
the positive. Okay, I got it.
And then you would do the
The same.
negative, and you do the same for the last row,
Yeah, so they would be
So-
all the exact same, just -1/2.
just -1/2.
So on exam, we're gonna write 8 of them. I mean,
I
for
would
the-
not ask you to do this on the exam. I would ask you if like this is a possible quantum number for an electron in energy.
Oh,
level 2.
okay.
So can you follow the rules? But no, I won't ask you to list all the quantum numbers because
Okay,
after
so-
this, they just get exponentially larger.
Yeah, because if you had even 4, it would be,
Insane.
Can
So
you
it's
tell-
actually, so if you think back to like middle school and they told you that the electrons go, well, there's 2 in the first level and then 8 in the next level and then 18 and then
Oh.
32. That's
Yeah.
actually the numbers of quantum numbers that are in each energy level.
so it's
So
just,
actually-
it's just squared with each energy level, basically.
Yes.
Yeah.
Yeah, kind of. Yeah.
So for this question, there only gonna be maximum 10 electron possible.
No.
Wait, I thought there's like a 10 sets of unique quantum numbers for electron.
For
when you-
electrons 0 to 10.
Yeah,
Yeah.
when we were looking at neon, so
Right.
Up
Yeah.
above there.
So when we're looking at neon, I said, right, there were 10 sets. So what we just did is actually listed all the quantum numbers for those 10 electrons.
So one set of quantum number could mean there's a one electron because they're not gonna have the same set of quantum numbers. So here is a 10 set of quantum number. I mean,
So this is
could-
10 different electrons.
so there
Because-
could be 10 electron.
Yes.
so then all of these numbers would be occupied if it was 10 electrons, because you have 2 from N1 and 8 from N2.
Exactly.
So okay, so, yeah, okay.
Yes.
So for neon, it's actually have 2 energy level, right? And n equals 1, n equals 2. And neon will have 10 sets of electron.
Right.
Oh.
So what we just did was we wrote out all of the quantum numbers for all of neon's electrons.
Okay. But if you had, like, let's say something that had 6 electrons, you'd
Mhm.
have 2 in N1, 4 in N2, and then you wouldn't necessarily know what numbers they were in N2.
right?
So-
You wouldn't
okay.
unless I specifically told you, right?
Okay, all right.
So you're not gonna ask it, write down quantum number for some
I could
element?
say write a possible quantum number for, but you're right, unless I give you more information and tell you specifically,
We
Which
can't
one
give
it's
you a
in,
definite,
wouldn't
we
know.
could just give you like one
Possible.
possibility.
that's exactly
Okay.
right. Yes.
All right, all right,
Yep,
I'm getting it.
awesome. Yeah, no, you're good. So I know class is almost over, so just bear with me for a minute, guys. This is like the complicated version. And then we'll do like writing these 1s2, 2s2, 2p6, so on and so forth, which is a little bit easier than quantum numbers, I feel. And so that's what we are going to do, not today, because we ran out of time, but we will do them on, when do I see you? Monday. But it's just doing electron configurations. So here's the deal. Since we haven't done those yet, okay, and I'm still trying to make sure that our test is before break because I don't want to have a test after break. Hang on, let me turn this thing off.